Now, our next topic is NAND gate. NAND gate. We've discussed about AND gate and OR gate, though we did not work on NOT gate. Those are basic logic gate. But universal logic gate, NAND gate, and NOR gate. So we are going to work on NAND gate and NOR gate as universal logic gate. So then, if you look at the diagram for the NAND gate, this is the symbol for the, it's the same thing as AND gate. So apart from the small knot at the back of the symbol. So, and it means that NAND gate is opposite of AND gate, the opposite. If you look at the truth table of AND gate, we are going to have an output if and only if both inputs are on. But the opposite of AND gate is NAND gate. So we are going to have on when any or both of the input is off. And we're going to have off if both the input is on. This is the truth table. And the equation, if you're talking about AND gate, the output equal to our output is equal to A, the first input multiplied by the second input. But if you're talking about the opposite, that means we are going to have bar. The opposite, that's the NAND gate. This is the equation for the NAND gate. So we now want to carry out the experiment and see. We are going to have two inputs and we are expecting an output. So we want to work on this NAND gate, do the practical. Yeah, let's go. We are given this, we have to find all these materials. We've already get it down, and look at this. This is the symbol for NAND gate. That's NAND gate, and this is the circuit given to operate a NAND gate. Let's look at from objective A. Identify and demonstrate operation of a transistor digital logic NAND gate and develop a truth table of logic function. Let's go now. Examine the circuit as shown in 8-2. This is the circuit given to us. We have to find two switch 1, switch 2, and those switch, they are our input. So input A, input B, and those input signal will be in two positions, either off or on. Off is 0, and on is 1. So we are going to have two signals, and we are going to have our output from here, which is C. So, and then in this particular, we have to use oscilloscope to determine our output, to look at our output. Switch 1 and switch 2 are what? They will be in two conditions, either 0 or 1. They are our input. And we're going to use, in AND gate, we use only 2 diodes. We're going to use 3 diodes in this one in order to reverse the condition of AND gate to become NAND gate. So we want to use this third diode to reverse the outcome from these 2 diodes, which will give us AND gate. We reverse it up to give us opposite value of AND gate to become NAND gate. So let's now see this circuit. Now, they said we should work on that. Let's see. The oscilloscope is used to monitor the output voltage at C for the various gating condition. For the various gate, for either on or off, we want to see the circuit. Identify the circuit as transistor. You now say from here, identify this circuit as transistor digital logic NAND gate. So because we have two diode forward bias, which we are going to have an output if you have both to be on, we are going to have, but because we have another diode that reverses the operation, and we have a transistor here that will direct the flow of current to the output. This shows that is an NAND gate. So that's about that. Connect the circuit as shown in 8-2. So we have to adjust the power to 5 volts. Set switch 1 and switch 2 to 0 position. Record in table 8.1. This table, we are going to have. We have the both switch is off. Switch, what will be the output? If one switch is off, one is on, what will be the output? If both switch is on, what will be the output? We are going to use here, we are going to connect our oscilloscope into the output. The positive to this and the negative of the diode to the ground. So we now want to see what will be the voltage, what will be the value of the voltage in our oscilloscope. We'll see we'll put our oscilloscope to voltage, DC voltage. We're going to write it to fill our table. I think we need to draw that table when we have switch 1, when we have switch 2. So then we will have our output voltage. So whereby we have 0, 0, 1, 1. We have 0, 1, 0, 1. We want to see what will be the value here. So now let's go and see our circuit. This is the circuit. This is the circuit. If you look at it very well, this transistor is this. This is the transistor given to us. Then we have to use a diode at the back of this transistor. The negative of the diode connect to the base, emitter base collector. This is NPN transistor. 2219, I think. Yes, that's NPN transistor. So this is emitter to the ground, the collector to our oscilloscope and a resistor here, and the base. So that's what we did here. Look at it. This is transistor. This is emitter base collector. So emitter is connected to the ground. This is my ground. This is the negative of the source, is meant ground, and this is positive of the source here. So then you can see the negative of the cathode is connected to the base. So and you can see these two diodes connected. So this is the circuit. We have switch 1 and we have switch 1 and switch 2. So we have it there. So that's the circuit, and we are going to use this oscilloscope to determine. We put it at the output. You can see that oscilloscope, the positive. So this is the probe for the oscilloscope. This is the positive side of the oscilloscope, and this is the ground, negative of the oscilloscope. So we are going to put that ground of the oscilloscope to the ground of our circuit, as shown here. Ground, GND, to the ground. We have done it, and the positive to the point, to the collector, where the point at which collector of the transistor and the 1K resistor met. This is the point. The point here. So this is the point. This circuit is this now. The circuit given to us, this circuit given to us is what we have done now. So we are now going to see what will be our output. Let's fill our circuit with 5 volts. I think it's 5 volts that we are asked to 5 volts from the circuit. So and we have 5 volts already from here. You can see that our circuit is 5 volts. When we on it now, we have already injected our circuit with 5 volts. So we have injected with 5 volts. Then let's now see what will be let's put all these switch. They are on 0. The switch are in 0. Let's now see what will be the value from the oscilloscope. Let's see what will be the value. Let's measure. So from the value, you can see that when we put both our switch into 0, we will have the maximum is 4.88 volts. You can see we have peak to peak from number 1, peak to peak value. That's the waveform. Though we are not looking for the waveform. We want to see the voltage, not the waveform. We have maximum, minimum amplitude, but that maximum value of voltage is what we need, which is 4.88 volts. It means that when we have our switch at 0, what we have is 4.88 volts. We have volt up already. Volt is up. Volt, this is what we need. We have what at our output, we have 4.88 volts when we have both switch at 0. Let's have our switch 1 to be 0 and switch 2 to be 1. This is our switch 1, switch 2. Switch 1 to be 0, switch 2 to be 1. Let's see what we have. We still have the same value, 4.88. Let's see. Okay, now the value has changed. We have 5.36 volts. 5.36 volts. So let's now take the switch 1 to be 1, switch 2 to be 0. This switch 2, let it be 0, and let's switch 1 to be 1. So let's see what we are going to get again. Let's reset it and see what the value that we are going to get from oscilloscope. Let's see. Let's see the value again. The value now give us 4.92 volts. That's the maximum value. I've used peak to peak, maximum, minimum. We pick that maximum value. This is 4.92. 4.92 volts. When switch 1 is 0, and when switch 1 is 1, switch 2 is 0. We have 4.92 volts. Let's now go to when we have both switch 1 at on. When both switch is on, let's see what will happen. We have put it to be on. Let's reset our oscilloscope. Let's auto resetting. Let's reset it back and see. Okay, let's see the value now. So what do we have now? We have 248 millivolts. That millivolt, it means 0.246. Milli means divided by 1000. So that means we have 0.248 volt. That's 0.248. That's 0.248 volt. 248 millivolt means divided by 1000. That's 0.248 volt. This is the table for NAND gate. The table 8 to 1 that we are asked to work on. This is what we are going to have. What we are able to use to fill our table. Look at the table given to us: switch 1, switch 2, and the output. So we'll use this value now. These values to fill this table 8 to 1. Have you all seen the table? So let's note that table, that value down. We use it to fill this table here. Let's see what else we are asked to do. Which combination of the switch setting resulted in an output voltage approximately equal to the 5 volt supply voltage? From the diagram, you can see that from that diagram, from that practical we just performed, you will discover that when any of the switch is 0, so we have the value approximately equal to, so this is the setting. When switch 1 equal to 0 and switch 2 equal to 0, so we have approximately equal to, exactly now. They asked us which combination of switch setting resulted to output approximately equal to 5 volt DC. The first one is this first combination. Second combination, when x1 equal to 0 and x2 equal to 1. That's second combination. And the third combination, when x1 equal to 1 and x2 equal to 0. So all these combinations give us the value. All these combinations: switch 1 0, switch 2 0, switch 1 0, switch 1, switch 2 1, switch 1 1, switch 2 0. These are the combinations that give us value approximately equal to the supply voltage. Is the output voltage close to 0? Is the output voltage close to 0 volt for the remaining switch? Yes. The remaining one, which is S equal to 1 and switch 2 equal to 1. So it's close to 0. You can see that we have 0.2 volt 8 volt. It's very close to 0 for the remaining one. So then I say assume, let's go to G. Assume 0 volt represent logic 0, 5 volt represent logic 1 in your circuit. Write logic equation for the transistor logic NAND gate from the result of the table. This. And remember, a NAND gate provide output logic. So let's use to write our logic equation now. It means that C equal to the same thing as equation of the AND gate, but we are going to put bar. That's negation of it. Negate. It's opposite. It's a reverse of AND gate. That's how the equation is supposed to be. So that is the reverse of a AND gate. That's that. Reduce the power supply to. Okay. Do we have any other? Okay. Use A and B as input and C as the output. That's what we've just. That's A and B as two inputs, C as the output. So this is the equation for the NAND gate. And then lastly, reduce the power supply to 0. Now you verify. Now we have done that one with oscilloscope. We are now asked to repeat the experiment using LED to carry out the operation. Let's now use LED to carry out the operation. Now reduce the power supply. We have done that. Now you will verify your logic equation using a light emitting diode. So as a digital logic readout, connect the circuit as shown in Fig A3. This circuit, we have to connect this circuit, the same circuit we've connected before. The only difference is that we are going to add another transistor, NPN transistor, to the output. So in order to direct the flow of current to our output device, which is LED, we have to use LED as an output device. We are going to use 150 ohm resistor to safeguard this LED. We need 1K here, 1.5K resistor. We need it here. So we have to connect. Adjust power source to 5 volts. Repeat switch setting of 8 to 1. What we have done in Fig table 8 to 1, we're going to do the same thing again. So we are going to have that table again. When we draw the table again for our 2 in 2B, that means we have in 2C, we have to draw the table again for 2C. So now say 2C, we're going to have switch 1, switch 2, then we are going to have our output. So we want to see maybe when we have 0, 0, 1, 1, 0, 1, 0, 1. So let's see what will be the output for what will be the output for each of them. So by using, we'll now see which one is on, which one is off when we put all this switch. That's what we have to do. Repeat the switch setting for this one. The LED will go out when driver Q1 is reverse bias with 0. So this occur only when the input gate condition are satisfied. Which combination of the switch setting cause LED to go out? Now let's now set the circuit and see which combination will give us will allow this LED to off and which one will let the LED to off to on. Then let's go. This is the circuit. This is the circuit. So this is the first transistor. So then we have the second transistor here. This is the second transistor. So and then we have diode. We have another 2 diode. We have switch 1. Let's say we have those 2 switch. Okay, they are 0. We have those 2 switch there. Switch 1 0, switch 2 0. So both those switch are at 0 position. So now this is our LED at the output. This is the LED. The first practical I use miniature lamp. I use this in our last practical because then I want to use LED, but I need LED that can withstand 5 volts. Most of the LED I have then they cannot withstand it, they will just blow. So that's why I use miniature lamp can withstand up to 5-7 volts. So but this kind of LED, which is 3 mm white LED, cannot withstand 5 volts. That's why I have to look for 8 mm. So this one is 8 mm white LED. So this one can withstand up to 5 volts. That's why I did not use LED for that previous one. I have to use lamp. So if you are to use LED has terminal. It has positive and negative terminal. This is negative. The short hand is negative. The long one is positive. It has positive and negative. Unlike miniature lamp, that one does not have any positive or negative terminal. So anyone can positive, one can be negative for this one, for this miniature lamp. But all LED they are like diode, which have positive and negative. It has an anode and cathode. Yeah? This is the cathode. This is the anode. This is the negative, and this is the positive, which is anode. This is negative, which is the cathode of this, because it's diode. The type of diode, LED is type of diode that give us light. That's what we use in this particular now. The negative. You can see the negative is connected to the collector of transistor. The positive is connected to 150 ohms resistor. As you have it in the circuit, come and look at the circuit. So the LED, the positive is connected to the 150 ohm resistor, while the negative of it, so this is the negative of it connected to the collector. This is the emitter, and this collector. This is the collector. This is the collector of the transistor. Emitter, base, collector. Collector is connected to the negative of the LED. So let's now see for that we are done. So let's see now what we let's put 5 volts to our. So as you can see that as I on the power, so we have switch at 0. Both 2 switch at 0. What do we have? We have our light common straight. That means we have on here. Exactly now, or we can call it 1. But let's put on because we are talking about LED now. Let's use on. Let's use on and off for our output. So we have on here, which is 1. So let's now off switch. Now we say switch 1 off, switch 2 on, switch 1, let's put it. Okay, both of them are 0. So when we have switch 1, 0, switch 1, 0, switch 2, 1, that's 2, 1. So look at it now. We still have that light on. We still have the light on. We have on. We still have it on. So when we have switch 1, 1, switch 2, 0. This is our switch 2, 0, switch 1, 1. We still have that light on. We still have that light on. We have it on. So when we have both of them at 1, 1. So this one is at 1. Let's say this one now at 1. What do we have? We have it to be off. It means that before we can have outputs, both of them, we must have either of them to be off. That means when we off this one now, so it will come on. When we put it back, both of them are now at, it will come off. When we off this one, light will come on. When we put it on, so light will go off. So that's that about that. You can see now. So this is the table given to us. This is the table we are asked to. So let's see what we are asked to do. Now said, okay, which combination of the switch causes the LED to go out? From your table that you draw at 2C now, you now used to answer that 2D. When switch 1 is 0, switch 2 0, we have on. When switch 1 0, switch 2 1 0, we have on. When switch 1 1, switch 2 0, we have on. Those are the combinations that give us LED. Okay, which of the combinations? Look at no mistake. I'm sorry. Which combination of the switch setting causes the LED to go out? Okay, it's only when we have switch 1 1, switch 2 1. That's what makes LED to go out. They don't say to go on, but to go off. That's what they are talking about, not to go on, to go off. So, and it's only one combination, which is S1 to be 1, S2 to be 1. That's when the LED will go out. That's our question 2D. We are done with that. Does this verified NAND gate logic question C so equal to A and B bar? There should be bar here. So then it's yes. So it has verified NAND gate for us. So refer to table 8 to 2, assume 0. So this table, if 0 and 1 position of means off and on. So then, and that logic O is indicated when the LED is off, and logic 1 represents when the LED is on. Complete the truth table for your transistor digital logic NAND gate for the various input conditions listed, if necessary use. So we have to fill this table now. So when we have on, we put 1. We use this table to fill this one. That means we are going to put 1 here, on, 1 here as well, which is on. This one is also on, we put 1. And this one is off, put 0 here. We use this table to fill this one now, to put 1, 1, 1, 0. And we are done. Reduce the power supply to 0. So we have reduced power supply to 0. So let's reduce power supply to 0. We have off our circuit. Then we are now want to verify OR gate. But before we go to OR gate, people will be wondering, why this, or this, what is it meant for? So it's very useful. Maybe by the time we'll see have time to talk, we'll talk about it much. But I want us to know that there is very applicable. So maybe let's look at automobile, for example, now our car. We can fix, this can be fixed to our door. The signal, the switch to our door can be fixed to this side of the gate. And this one can be fixed to our selector, gear selector. So at park. So then this one will now be fixed to our ignition. So it means that if you open the door and we do not put our gear to park, so there will be an ignition here, light, that shows that when there is light here, it shows that you cannot ignite, you cannot on that car. You can only on the car if you've closed the door and you've put the gear at park. That's when light here will go off. When you on this one, when this one is on, the door is closed. When this one is on, the door is closed. Exactly. That's when this one will go off. When when the light of the ignition now go off, that means you can start the car. But when the ignition will only show a red light if any of this is 0. If this one is 0 and this one is 1, this one will become 1. Exactly now. So it's going to, let's look at the table. Okay, this is the table. So if you have closed the door, this one has become, if you close the door 0, you've put your path to the, you put it to P, your gear selector to P is 0. If you open it down, it's on. Light of this one will on. If this one is 1 0, this one is also 1 0. So when you close the door, it becomes 0. When you put your gear to park, it becomes P, and this one will now become what? It now become on. But whenever any of this is open, so there will be an ignition. So it's only when both of them are now at 1, the door has been closed, 1, the gear has been put to park, 1. That's when this one would now go off. That's when you are going to start the car. That's the application, the logic gate for new model of the car. We're using now. When you close door, when you put your park, when you close the door, that means 1. When you put your gear to the park P, that's 1. So when 2 conditions are satisfied, then so the safety ignition, safety, we call it, we use it in safety for safety purpose. So that's when the ignition red light will now go off. That's when you can be able to start anything. It's also used in industry, whereby the machine will only start when you have, you have closed the door of that machine and you have, you've pressed the alarm button. So when the 2 conditions are satisfied, then you're now going to, that's when the output will now, come on. So that's that about that. That's when it's going to, because this one will be like a switch that will off your circuit. But when this one is now satisfied, they are on and on. It will now off, can allow the current to pass. So that's that about we'll talk more about the application by the time we have class. But I just want you to know, because some people say, what's on this on off 0? So it's just to operate some activities automatically. That is this. That's that about that. Let's go to OR gate. Let's go to OR gate now. Now let's check NOR gate. NOR gate. NOR gate means OR gate, the reverse of OR gate. So examine from number 3A now. Examine the circuit shown in Fig 8 to 4. This is the addition of switch 1 and switch 2. We are talking about all these the previous circuit given to us, I think. And then so we are going to follow the same procedure we follow for NAND gate. So we are given a circuit, Fig 8 to 1. So we have to construct this circuit and see. Then they now ask us question here. Let's see what identify the circuit as a transistor digital logic NOR gate. So it's NOR gate because the 2 cathode of the anode is what has been grounded. So why the positive has been, so this shows that is NOR gate. It's only if we are talking about OR gate. So if any of the switch is on, so you are going to have an output. So because this one will give us ground, and this one, when we on this one, we are going to have positive from here. So this is OR gate because we have the two anode of the 2 diode grounded. So this shows that is an OR gate. But because we have a transistor to reverse the operation, so it has turned to what? Turned to NOR gate. That is reverse operation of the OR gate. So we are going to construct this circuit now and see. Inspect the circuit shown to provide 0 volt output when either or both inputs are 5 volt. Certifying the logic for a NOR gate. C equal to or bar. There should be a bar here. Diode and resistor comprises OR gate, and transistor Q1 is a NOT circuit which together form a NOR gate. So this transistor give us NOT. It negates the operation of OR gate. So, and we are given this circuit, and OR gate, this is the symbol, is the OR gate with the negation with the 0, this NOT at the back shows that this is NOR gate, and this is the table. Is when we have both circuits to be 0, so we are going to have an output. If any or both of the input is on, we are going to have off. We are going to have that's NOR gate. So that, and this is the equation for it. C equal to A plus B bar. So that is negation of A plus B. So that's what we are going to. So let's see what we have to do here now. So we are going to have switch 1, switch 2, and the output. So let's say we have switch 1, switch 2. So when we have 0, 1, 0, 1, 0, 0, 1, 1, we want to see what we are going to have at the output. So we want to see what we are going to, the value. When we are going to use oscilloscope as we use for NAND gate. We'll do the same thing for our OR gate and see what we are going to have. Yeah, let's go. This is the circuit. So we have the two switch. We have diode, the positive connected together, the negative of it, that's the cathode side. So feed to the base of the transistor. So then this is our oscilloscope. We are going to use the negative of oscilloscope to the ground. Let's ground our oscilloscope. Then the collector of a transistor, put positive there. The positive of the push it there. Then let's see. Okay, let's inject 5 volts to our circuit. So let's now set our. So let's measure. You can see that what we have for maximum is 4.92 because we have our switch to be 0. Switch 1, 0. Let's see our switch. Switch 1, 0. Switch 2, 0. Switch 1, 0. Switch 2 at 0 point. And what we have from there is, look at the maximum value from oscilloscope, 4.92. Let's record that one. 4.92, closer to the value of the input value, which is 5 volts, very close to the value of 5 volts. Have you seen it now? So let's see the next one, which is switch 1, 1, switch 2, 0, switch 1 is 1. Let's put it to 1. And switch 2. Let's set our oscilloscope again. Let's reset it and see. Let's do the measurement. Let's measure. What do we have? Maximum, like let's see the value. 15.8 millivolts. 15. That's 0.0158 volts. So that's 15.8 millivolts. 1, 2, 3. That's 0.015 volts. So that's what we have. So let's now go to the next one. When switch 1 is 0, switch 2 is 1. Switch 1, 0, switch 2, 1. So let's go back again and set our oscilloscope and see what. Let's measure and see what we have. We have 3.44 millivolts. Max. And what we have is let's see. Okay, maximum. What we have is 19.0 millivolts. 19.0, that's 0.019. So that's 0.019 volts. 19.0 millivolts. That's 0.019 volts. So let's have switch 1, 0, switch 2, 1. Switch 1.
That's
what we've done. Okay, we've done that one. So when we now have switch 1, 1, switch 2, 1. Let both of them be at 1. Now let's see. Let's now set our oscilloscope. Let's set it back and see what will be the value. what do we have? We have 16.0 millivolts. 16.0 millivolts. We have 16.0 millivolts. That's 0.016. That's it. Yes, it's 0.016 volts. Have you seen it now? So from the equation now, you can see that we only have value closer to the input value, which is 5 volts, on when we have both switch at 0. When we have both switch, that's why we have output. Others give us value close to 0 volts. So that's what we have to do here in fig 8.3, and we have set switch 1 and switch 2 combination to here. We have done that. Record the output voltage for each combination. We have recorded it. That's what we've done. Look at the result of the table. Which combination switch setting result in output voltage approximately equal to the 5 volt. We have seen it. It's only one combination, which is when switch 1 is 0, switch 2 is 0. I think that one is done. Is the output voltage 0 for the remaining switch combination? Yes, I think that one is simple. From the result of your measurement, write the logic equation for the transistor digital logic NOR gate. Assume 0 is 1. Okay, I think we've done that before. So I think this is it. This logic equation. C is equal to A plus B bar. So opposite of the OR gate. So this power supply to 0. So we have to off our circuit then and try the OR gate again with LED. We're going to use LED now. We're going to control this circuit, and we're going to control this circuit. Let's control this circuit now. Right now, now you all verify your logic equation using the LED as a readout. Connect the circuit as shown in fig 28 to 5. So which is fig 8 to 5. Not is a mistake. So this figure, this circuit, we have to connect this circuit here. So let's now see what we will do. So fig 8 to 5, we have to connect the circuit as we have it in fig 8 to 5, this circuit. I just power supply to 5 volts. So this circuit, I put 5 volts, repeat the switching setting of the one we did previously for NAND gate. We have to do it for NOR gate. So which combination setting caused the LED to go out? Let's now see. This is the circuit. We have switch 1, switch 2, the 2 diode. Now before we have cathode connected to the switch, but now we have anode connected to the switch and the cathode connected to the base of the first transistor, second transistor, and then we have our switch outside here, the way we have it for the NAND gate. We just have to change. The only difference is that we reverse the operation of diode, and then instead of having another diode there, we have a resistor at it there. So that's that about that. Let's see now. So now let's see which combination will give us for all gate now. When we have switch 1, switch 2, so when we have 0, 1, 0, 1, 0, 0, 1, 1. Let's see what will be the output for. So let's start. So this is our circuit. We have it on. We have it powered, and our switch is, let's put it to 1, and this one also 0, 0. Let's see. Look at it now. So when we have both two switch at 0, so 0, and this one also 0 at point 0. So at point 0, so we have our bulb, our LED to be on. The LED is on. Now when you have the two switch to be 0. So let's now have switch 1 to be 1, switch 2 0. Switch 1 to have 1. So switch 2 to be 0. You can see that our LED is off. We have off. We have off. Let's have switch 1 0, switch 2 1, switch 2 1, switch 1 0. So what do we have? We still have it to be off. The LED is not on. So when we have both switch to be on, let's see what will happen. So now we have both switch on at 1. Well, you still have LED to be off at the same time. We only have on when both switch is off. You can see now, if both switch is at the 0, both switch at 0, that's when we have our LED to be on. So that's for NOR, that's operation of NOR gate. Whenever any of the switch is on, so or both is on, we are going to have off at the output. So let's now see. So we have done that. Which combination of the switch setting cause the LED to go out? I think we have seen it now. So when we have switch 1 to be, it go off when we have switch 1 to be 1, S2 to be 0, S1 to be 0, switch 2 to be 1, or when both switch are off. So we have it to be, so that's what makes the switch to go off, to go out. Does this verify NOR gate logic equation? Yes, it verifies the logic NOR gate. Refer to table 8 to 4. Complete the truth table of logic function of transistor. Confirm your result using test. We have to form another table here. This kind of, okay, we have been given table 8 to 4. This is 8 to 4. So we are going to use our on will be 1. That means we are going to have 1 here. And we are going to have 0, 0, 0, 0. Only this one will have 1. If you are to refer to our table at C, we are going to have this table in C. So we now use it to fill the table at table 8 to 4. Just put on 1, remaining 1, 0, 0, 0. Only this one will be 1. So then reduce the power supply to 0. So we now off our source of power supply. We'll off it and our light is off. Then we'll read our summary from there. So we'll still talk more about that when we have class. Then we'll look at our quiz. So we'll check the quiz. Most questions we are asked to solve as simple questions. So that's that about that on transistor digital logic gate, NAND and NOR gate.